All right, this is the first hour of Physics 1C for November 8th. Let's go full screen here. Okay. So last time, we talked about sources of magnetic fields, right? And I am streaming, right? Everything's going okay? It looks like it's okay. What did we learn last time? We learned that if you have a long straight wire that carries a current I, and you come to some position that is a distance r away, perpendicular distance r away, we said that there is going to be a magnetic field at this location. What direction does it point? Can you all tell me? What's the direction of the magnetic field due to this current carrying wire going to be at this location? We know the size is this, right? But what is what's the direction? Is the into the page or out of the page? Into the page is correct. So there's a magnetic field that's produced at this location. It points into the page, and if you don't remember how to do that, you run your thumb in the direction of the current, and then your fingers sweep out the direction of the magnetic field. So from the perspective, I don't know if this will look good from your perspective because of the camera thing, but thumb going this way, your fingers would swing and hit the screen, right? Which means that the magnetic field goes into the page like that. Okay, and then the size of that magnetic field is mu naught I divided by 2 pi r. So combining that with the force law, the Lorentz Force Law that we learned, which tells us that there is a magnetic force that's created on a current carrying wire, where if you take the current and you multiply by the direction in which the current is moving and create a vector for that for the length of the wire, and you cross product that with the magnetic field, this gives you the magnetic force placed onto a current carrying wire. So what we can do is we can look at the force between parallel wires, and we'll do that in this problem here, but let's talk about the theory first. So suppose that I have two wires. Okay, so we draw one wire like this, and we have another wire that's parallel to it, that is directly below it, like that. So two parallel wires, and let's say that they carry currents in the top that I call I1, and in the bottom, this one carries a current that I call I2. We can ask the question, what is the force between the wires? Okay, what kind of force does wire 1 place on wire 2? Is it attractive? Is it repulsive? Etc. So in order to do this, what we're going to do is we're going to say that wire 1 is going to create a magnetic field at the location of wire 2, okay? And you all tell me, again, it's always good to test your understanding of the right-hand rule. What's the direction of the magnetic field here due to wire 1? So wire 1 creates a magnetic field. Does it go into the page or out of the page at this location right here? Into the page. That is correct. Let's say the length of our wires is L, and let's say the distance between the wires is A. I forgot that. Into the page, exactly. So we know that there's a magnetic field created right here. I'm going to call it B1. That same magnetic field exists at all points along here because the two wires are a specific distance apart from each other. So we call that magnetic field B1, right? Now let's reverse the situation. And let's ask, for wire 2, there's going to be a magnetic field created at the location of wire 1. Does it point into the page or out of the page? So I'm asking about what we're going to call B2, which is going to be the magnetic field created by wire 2 at the location of wire 1. Is it into the page or out of the page? This one's going to be out of the page. And the symbol we use for out of the page is dots, right? So B2 points out of the page. Now, the next thing to do is to say, okay, if I know that there is a magnetic field B1 at the location of wire 2, then there must be a force, according to the Lorentz force up here, created on wire 2 due to the magnetic field B1, okay? And the size of that force, which I'm going to call the force of wire 1 on wire 2, is going to be equal to the size of the current flowing through wire 2 multiplied by L, which is going to be the length. I guess I could say this is like a vector and it points this way, the direction of the currents. And then we have to cross product that with the magnetic field produced by wire 1. Now you all tell me, what direction according to the right-hand rule, what is the direction of F12 going to be? Is it going to be up or is it going to be down? What's the direction of this one going to be? So use your right-hand rule. The force of wire 1 on wire 2. Is it going to be attracted to the top wire or is it going to be repelled from the top wire? Up. That's right. So we know that the force here, in this case, is going to point up. So we're going to call that the force of wire 1 on wire 2. Okay. Now I'm using multiple arrows here to indicate that it's a force on the whole wire. But really we could draw one force vector for F12, but we're just kind of saying that the force is evenly spaced across the wire. Okay. And again, if you don't remember how to do that, you take the direction of the current, which is this way. You rotate your fingers into the direction of the magnetic field, which is into the page. And your thumb will be pointing in the direction of the force. I will let you all convince yourselves that, well, you know what? Let's stick with that. We'll just talk about just this, and let's not add too many things. Okay, so what's this going to be equal to? Well, we know the size of the magnetic field created by wire 1. Okay, so let's just talk about the magnitude of this force. So this is going to be I2 times L times the size of the magnetic field created by wire 1, but we derived that last time to be mu naught I over 2 pi r. So we use mu naught. Here we're going to put I1 divided by 2 pi times the distance between the wires, which is A. And with a little bit of rearrangement, we will get to our final answer here, which is going to be that the force per unit length is equal to mu naught times the product of the currents, I1 times I2, divided by 2 pi times the distance between them. And this is the force between parallel conductors. Does anyone have any questions? So this is the force of wire 1 on wire 2. But due to Newton's third law, forces can't exist in isolation. Why is B2 pointing in again? Take your thumb and point it. Wait, B2's pointing out, Evan. B1 is in. Okay. B2's pointing out. So you have to, I can tell you, but you have to do this. I can't emphasize enough that like what I say is something you have to do yourself. You can't just visualize it. You can't think about it in your brain. You have to actually do it. So you run your thumb along I2. That's going to tell you the direction of the magnetic field. It curls around I2. So on the top of the wire, your fingers curl out of the screen. So that's why B2 comes out. And if I would look on the other side over here, at this location here, B2 would point in. But at the location of wire 1, B2 is coming out. Okay, hopefully that made sense. So just, I think of it as like gripping the wire, and then you just kind of rotate your fingers around. Okay, one other thing to mention about this, like I said, Newton's third law tells us that forces can't exist in isolation. If this is the force of object 1 on object 2, the force of object 2 on object 1 should be the same. And I'll leave it to you to prove for yourselves, just to save a little bit of time here, that there's also going to be a force that points in this direction, and that force will be equal and opposite. These two wires are going to be attracted to each other. We can call that the force of object 2 on object 1, and we know from Newton's third law that the force of 2 on 1 has to be equal to the negative of the force of 1 on 2. That is to say, they have to be equal and opposite, and you can prove to yourself that you get exactly the same result whether you find the force from 2 on 1 or 1 on 2. And that's what the result is right there. If you all remind me while we're doing the lab on Wednesday, I have a really nice demo of this that I can show you, where you can actually see the wires like be attracted and then be repelled. Oh, that's the other piece of this. The force between these cut conductors is attractive when the currents are in the same direction. and it's repulsive when currents are in opposite direction. Okay, so if I had a situation where I had a current I1 that goes this way, and I had a current I2 that was going this way, that would be opposite directions, and now you can prove to yourself that the force is now going to be like this. F on this one is this way, and F on this one is this way. Okay? So you can prove that using the right-hand rule and stuff. I'll leave it to you to do so if you want to. All right, so let's do a calculation using this equation, very simple equation to use. It says 2 straight parallel superconducting wires carry Yes, you do the same thing for B1. Point your thumb along the direction of I1. Above, the magnetic field is going to be coming out of the page. And then wrap your fingers back around. It kind of hurts your hands to do this, probably. But then on the bottom, below the wire, the magnetic field for B1. God, it is so hard to do this stuff when I can't stand in front of you and show you these things. And also when I can't point on the board. Like, I can't point to the board except for with this thing right here. But the point is that... Here. I find it easiest to think about it like this. Suppose I have a current and I call it I1, right? And I say that it goes into this, it comes out of the screen. Then the magnetic field for this is going to come around in a circle like this. The relationship between currents and magnetic fields is circular. Okay? So if the current's going this way, the magnetic field sweeps in a circle around it, right? So take that same idea, right? And then for I1, which is pointing to the right here, your thumb swings around. Is I2 flowing left or right? It's flowing left. Is this not clear? I2 is right and I1 is right. It was drawn left? What are you talking about? Oh my god, am I just confusing you all? I'm just going to stop for a second. I'm going to stop talking. I'm going to let you all ask questions. This I2 is left. This I2 is right. This is right. When I have a wire like I1, right? Let's draw it over here so it's by itself. If I have a wire like this, I1, okay? That's the same direction as it's pointing up here. Above the wire, the magnetic field is going to come out of the page. And below the wire, the magnetic field is going to go into the page. Right? And the way you can understand that is if you grip the wire, your fingers swing and rotate out of the screen from above and then back into the screen from below, creating a circular type of magnetic field that if you could draw it out of the page would come out here and go back in there, right? It would come out here, go back in here, out here, and go back in here. Does it help you to understand it? And in order to actually see what's happening there, you swing your fingers in those directions. Seems like you figured it out, which is really good. All I can say is that this isn't specifically directed at you, Evan, but for all of you that get confused with this kind of stuff, you're not holding me up. This is the kind of stuff, what we're doing right here, this social interaction where you're confused and I help you to resolve that confusion, that's the only reason you even show up to class. Let's be honest. Like, that's why you're here. For all of you, I hope, is to get some kind of, like, interaction with me where you can clarify things you don't understand. So you don't have to apologize, Evan. That's a good question. It's really hard to understand. And it's really hard to understand when I'm trying to teach it over a screen. But regardless, yeah, maybe this helps. Maybe drawing these kind of lines like this help a little bit. But one thing I'll say is that it's very valuable to read the textbook. I'll just put it that way. Spence, I'm sure you probably do read the textbook, but you got to read the textbook and like really sit there and think and make sure you understand how your right hand works to show you these things. Alrighty, let's do this problem. 2 straight parallel superconducting wires, 4.5 millimeters apart, carry equal currents of 15,000 amps, but in opposite directions. What force per unit length does each wire exert on the other? 15,000 amps, huge amount of current. So we're going to be using this equation. Force per unit length is what we want to calculate. And force per unit length is going to be equal to mu naught. If you don't remember, mu naught is a constant. It's equal to 4 pi times 10 to the minus 7 Tesla meter per amp. If I'm wrong about that, then the units will not work out. We'll check to make sure the units are right, though, in a second. Our currents, I1 and I2, are 15,000 amps apiece. So we'll put 15,000 amps times 15,000 amps, and then we divide that by 2 pi times the distance between the wires. So 2 pi multiplied by 4.5 millimeters, which would be 4.5 times 10 to the minus 3 meters. And we hope that this gives us units of force per unit length. Let's calculate what it is real quick. I get 10,000 newtons per meter. And we'll check the units out. But anyone have any questions? So a Tesla, what are the units of Tesla? Well, we have this equation, FB equal to ILB, the Lorentz Force Law, right? B then should be the units of newtons divided by amps times meters. So that's what the units of the magnetic field are. It's the symbol for units, Newton per meter amp. So what do we have here? Total, we have, that would be Tesla meter over amp. Here, let's write out all the steps. So Tesla meter over amp times amps, that's amps squared, and then divided by meters in the bottom. So Tesla is newtons over meters times amps. So now we have amps squared here, and then we have amps squared per meter. Oh, I left off a meter. There was still a meter left over here, my bad, from that meter. We plug in Tesla, which was newtons over amps meters, so we got newtons over meters from that, and then we got amps squared. And I think you can see that the units cancel out correctly, that we get newtons per meter, which is what we want. Okay, any questions? Pretty easy. Okay, so it's very nice that we can now understand what the magnetic field of a long wire is, and then we can use that idea to construct the field, the force between two parallel wires. Speaking of which, if you have an extension cord, do I have an extension cord that I can show you this with? Where's the fiber? If you ever look at an extension cord, you may notice that there are two wires in any extension cord. So like, let's say you have something that plugs into the wall. Okay, so you got a little plug here, right? There's always going to be two wires. They're usually split down the middle, kind of like this, right? If you think about it, there's usually current flowing. Let's say this is the positive side over here. So there's usually current flowing in this direction, and then it flows through your system, like maybe through a light bulb or something like that, and that same current flows back here, right? So in a normal electrical system, you're always going to have these kind of parallel currents here, right? Current this way, current this way. So that means that there's technically a force that's pulling these things apart. But if you go and calculate what the size of this force is, you'll find that it's very tiny. So it's not something you really have to worry about. But if the currents get really big like these are, it's conceivable that you could have a sizable force here that could cause the system to have some mechanical effects you might need to deal with, such as, I don't know, high voltage power lines, for example, right? When you see power lines running across the country, you know, you see these, usually see like two lines, right? Connecting between like two poles. You have, you've got one pole here and you've got another pole back here. And you've got these wires and they also carry currents and probably same kind of thing, or one current's going this way and the other current's going the other way. And so there should be a force on these as well, and that force should drive them apart, right? So, you know, one thing about these is that they're usually placed really far apart from each other, right? Not really far, but they're not like a few millimeters apart from each other. They're probably a few feet apart from each other. And since that number shows up in the denominator, that'll reduce the force they feel. In addition, you have this overall factor of 4 pi times 10 to the negative 7 that reduces the force. But nonetheless, it's something you have to think about. If the current gets high enough, then the force can become pretty sizable. If you had a force of this size, that would be very noticeable. The wires would bend away from each other and may create stresses on the poles that are holding them and stuff like that. Something you'd have to think about. Okay, so like I was saying, we now know how to find the magnetic field of a single current carrying wire as long as it's straight. But what we're going to find is that a lot of the systems that we deal with are going to involve wires that are shaped like coils. So we'd also like to be able to find the magnetic field created by a loop of wire. Okay, so that's the next thing we want to do. The magnetic field of a circular loop. Now here's the picture, and we're gonna rely on it, but I want to try to draw it first because I often find the act of drawing it is part of what helps students to understand what's happening. So circular loop, right? So we're gonna start off with a loop. We're gonna imagine that our loop is kind of angled a little bit, so it's still a circle, even though it looks like an oval, but we're kind of imagining that it's kind of, we're looking at it kind of like an edge. Like, you know how if you look at a coin straight on, it looks like a circle, but if you tilt it a little bit, it starts to have this kind of oval feature to it. So that's the idea. We've got this ring here. Now it's going to have to carry current, so there's going to be current flowing through here. The book does this way of like, let's just imagine there's current flowing around here like this. Next, what we want to do is we want to draw a line to represent like an axis that's coming out of the page. So this is going to be like our x-axis here. That's the x direction. And we're going to label the radius of our loop here to just be A. And what we're going to do is we're going to find the magnetic field. Remind us what we're doing. Magnetic field is circular. We're going to find the magnetic field here at point P. Okay, so we want to find the direction of the magnetic field at point P when we have current running around in a circle like this. And to do this, we're going to use this thing that we talked about last time, which is the Biot-Savart law. And I just copied it from our last notes. This is the Biot-Savart law right here. It tells us how we find the magnetic field for any shape of wire. And because a circular loop has a lot of symmetry to it, we should be able to easily use this. This is quite tricky, this derivation. I think largely because I think it's really hard to visualize what we're doing here, but we'll try our best. So, what do we need to do in order to use this equation? Well, the first thing we need to do is we need to label a piece of our loop. Okay, so we've got our loop of wire right here. It has a current flowing through it, just a little circular loop of wire, and we're going to label this piece right here to be ds. All right. Keep in mind that that loop that we have there, we have to kind of imagine that it's coming out of the page now. The next thing we need to do is we need to draw an r vector. And that r vector always goes from the ds vector, the line element of the current, to the point P. So now we'll draw a vector from here to here. And we'll get it right on that edge. All right, so that is our r vector. And then r hat, of course, is a shorter vector that has length 1 back here. Now, the first thing that we have to do is to figure out what ds cross r hat is going to be. And specifically in this case, we have to think about what direction it points. So if we imagine, I'm going to give you a kind of a side view picture. Call it the edge view. Because I think it'll help you to understand what's going on here. If we were to take our circle, which is like I said, it's like a coin, and we look at it on its edge, it would just look like a line, right? So here's my circle. It'll just be a line. We'll actually use a straight line for it. So let's say this is the edge of my loop right here. We'll make it red as well. So that's the edge of my loop right there, right? The current on this side is coming down, let's say. Oh, no, it's going up. We're looking at the front edge, right? So my bad. Come on, let me undo. It's not letting me undo. Whatever. So we're looking at the front. This will be the front edge right here. So the current flows up, and then when we get to the top where that ds is, our ds is going to be going into the page here, right? So there's ds, right? And then our point P is somewhere over here. So here's P. And of course, A is the dimension of this. We'll say this is our center point right here. Let's draw our, I'll put the center as a dot on here too. Let's draw our axis this way. That's our x direction. So that was A, and then R, so this is point P. And then R is going to be a vector from here to here. Okay. So there's R. Okay, from this picture, it should be pretty easy to see how this works out. And I'll draw R hat on here too. R hat would be this way. Okay, so now can you all tell me, I don't know how easy it is to describe, what is the direction of ds cross R hat? ds cross R hat. So use your right-hand rule, right? Point your fingers in the direction of ds, which is going into the screen, right? And then shift your fingers so that they're pointing, so your palm points in the direction of R, and then just rotate your fingers from ds to R hat. And tell me, what is the direction of ds cross R hat? Two people say down and left, southwest. I'm pretty sure that's correct. Pretty sure that's right. Because if you point your fingers in the direction of ds, face your palm in the direction that R is going, right? Then if you do ds cross R hat, your thumb points diagonally this way. Hopefully you can all see that. It's definitely not easy to see. So at the location of P, we would draw a vector this way to represent what we would call dB. Let's use a dark purple for that or something. So this is going to be our dB direction here. And it needs to be at a right angle. This has to be a right angle. And that is going to be dB. Convince yourself that that's the truth. Now we could also come to the exact opposite side. Yep. ds cross R, thumb point southwest. Exactly. Now we could, likewise, we could have come to the bottom down here, right? Where our ds vector over here would be pointing in that direction, right? Tangent to the circle. But that's coming out of the page, right? Why is undo not working today? It's really, really annoying. Out of the page, right? And then we could have done the exact same thing, right? We could have taken a vector here. We could have drawn our R vector here, right? And we could then do another ds crossed R hat thing here, right? So this is ds. And this would be R hat. And now if you do ds crossed R hat, what direction do you get now? So ds is now this way, R hat is this way. I think you get northwest now. Would you all agree? Convince yourself that you now get northwest. Do you all agree? Up and right. No. This way. ds, you have to go. This is one of those where it's easier to stand up and turn around. Because your ds is this way, out, and your R hat is this way. It's a lot easier if you stand up. If I completely turn around, you can't see what I'm doing now. It's definitely easier if you just turn around. Okay, do you all agree? Up and left? It's hard to see, but we got to keep going. Now, the key thing here to understand now is that similar to other times when we've done calculations like this, what happens to, let's say, the y components now of these two things? The y components are going to cancel out, right? Because this is going to have a y component that goes this way. This is going to have a y component that goes this way. So they'll cancel, right? The dBy's will cancel. Which means that all we need to do is to calculate the x component, okay? All we need to do is to calculate the x component. So to do that, we can say dBx should be equal to dB times, we need an angle. What angle are we going to use? I think this angle works just fine. If we call this angle theta, then I would argue that this angle here is also theta. Likewise down here. And if we call this position here the x, so we call this distance here x basically, from here to here, then we can say that, well, we want the x components, right? So if theta is this whole thing here, we're going to do dB times, what do we, sine or cosine here? Something theta. Do I put sine or cosine here if I want to get the dBx in this case? I want this component, basically. I think we want cosine, I agree. Okay. And we can say that cos theta should be equal to x over r, or that cos theta is equal to x over x squared plus a squared to the 1/2 power. And then what's dB? Well, dB is this equation up here. So it's mu naught I over 4 pi r squared. We need the magnitude of ds cross r hat, so we'll have to talk about what that's equal to. ds cross r hat, and then multiplied by cos theta, and that should be what dBx is equal to. So let's talk about this piece here. Or let's write it over here. ds cross r hat magnitude. What is that? Well, this is going to be equal to the magnitude of ds times the magnitude of r hat times the sine of the angle between them. Let's call it phi. This part is really hard. Well, it's hard if you look at this picture. It's probably not so hard if you look at the picture on the right. So it's probably easier if you look here. What's the angle between ds and r hat equal to? What is the angle between ds and r hat? 90, right? Because I have a vector here, ds, that goes into the page, and then I have another vector, I'll use my phone, I guess, r, which goes this way, right? So they're at right angles to each other, right? So if ds goes in and r is this way, then we turn it this way, you can see that it's a 90-degree angle, right? Can you all see that? So what's the magnitude of r hat? Well, the magnitude of r hat is 1. So this whole thing then is actually just equal to the magnitude of ds, which is just ds. Or we could say that ds, which is also equal to like 80 theta if we want to. All right. But I think in this case, it doesn't really matter what we do. No, it's not 80 theta. I'm sorry. That's not right. Ignore what I just wrote. Sorry, I didn't mean to confuse you. So ds cross r hat actually just ends up being equal to ds. That's it. So putting these together then, what we have is mu naught I over 4 pi times r squared times ds times cosine of theta. But we said that cos theta was equal to x over r. So this is going to be mu naught I ds x over r. But there's already an r down here, so we'll have an r squared times an r. So we're going to get mu naught I over 4 pi times r cubed times x times ds. And now what we want to do is integrate both sides so we can find out what this is equal to. So we're going to get that b sub x, the x component, is going to be equal to. So of all of these things here, actually everything is a constant in this problem, if you look at it. The distance r from a ring to the point P, as long as the ring is situated such that the axis is coming perpendicular here, then the distance r from here to here would be the same as the distance r from here to here. Doesn't look like it on a three-dimensional picture. Or the distance r from here to here. All of those r's would be the same, right? So we can pull that out of the equation here. So we're going to have mu naught I over 4 pi, those are all constants, times r cubed. And the x is also just a constant distance away from the wire. So we're really just left with the integral of ds. But the integral of ds just means to sum up all the ds's on the line. So what's that going to be equal to? What's the integral of ds going to be equal to? Two pi a, exactly. So we'll have bx is equal to mu naught I x times 2 pi times a. After all, the radius of this thing was a. And then we divide that by 4 pi times r cubed. And the final thing that we can do is we can replace now r with x and a. So we can write it as mu naught I. The 2 pi's, one of the 2 pi's will cancel, and there'll be a 2 left over in the denominator. So we'll have mu naught xa divided by, what do we have left over? Just a 2, and then r cubed, which is going to be a squared plus x squared squared to the 3/2 power. Because r is equal to a squared plus x squared to the 1/2 power. And that's our result. This is the magnetic fields due to a loop of wire on axis. And a natural thing to do from here is to want to find what is the field at the center. Where x is equal to 0. Hold on a second. Cos theta was x over a, right? Did I make a big mistake here or something? Oh, I know. I see what I did wrong. My cos theta was wrong. My cos theta is wrong here. The reason it's wrong is because the way that I drew this. You look in the actual triangle here, this is theta, so the adjacent side is A. I'm so sorry. So basically, I'll do a different color for these. This, all should be A's. That should be an A, that should be an A, that should be an A, that should be an A. And in our final result then, okay, some more. So this should be an A, an A, an A. So A here, A here. Does it actually just become A squared? Yep, that's the right answer. Okay. Now we can say, what is the field at the center? I apologize for that. The main mistake was just wanting to find this cosine theta. Sorry. It's really easy to make mistakes with this stuff. All right, so then finding the field at the center, you set x equal to 0, and what you're going to get is that b is equal to mu naught I. There's an a squared here. When I set x equal to 0, you're going to get a squared to the 3/2 powers, which is a cubed. So you'll have mu naught I over 2a. Nice, simple result. Complicated derivation, simple result. Common thing in physics 1c. So that tells us that if I have a ring of wire and I have a current flowing through it like this, first of all, from the right-hand rule, we know that the direction of the magnetic field at the center of the loop is going to point out. Again, you can verify that by sweeping your fingers in the direction of the current your thumb points out, or you can grip it and you can show that it always on the inside the magnetic field is going to be coming out. So that's the direction, and this is the value, mu naught I divided by 2a. Anyone have any questions? This is the picture the book uses. I realize now that their current is going in an opposite direction, but if this picture helps you, maybe, I don't know. Any questions about this? Are there harder versions where ds cross r hat isn't just ds? Probably. I mean, definitely, yeah. Also, this may be something that has, I mean, I think the easiest thing is just say yes. Although you don't have to really do all of these calculations yourself. Usually we just, I just give you the results. You don't have to actually derive anything with the bias of our law, because I've always thought it was just a little bit too tricky. All the different three-dimensional vectors and stuff you have to deal with. That being said, I think some other teachers might have you do calculations with it, and I know that there are lab manual problems where you have to use the bias of our law, but I didn't assign any of them for you, so you don't need to worry about it. I do know that when Hacking used to teach this class, he would assign a lot of those problems. Maybe Dr. C does too, I don't really know. And yeah. Now, one other thing about this, the nice thing about loops of wire compared to long wires, right, is that you can just stack loops on top of each other, right? So what you can do is you can say, suppose that I have a loop of wire, but it doesn't just stop. It's just a continual loop of wire, like this, and we get a whole bunch of like loops of wire, right? And then, the current comes in this way, maybe it goes out this way, right? So I've got current flowing in here, I've got current flowing out there, and in the middle I just have a loop. Bunch of loops of wire right here, right? Maybe in loops. Well, then the magnetic field that's created at the center right here, which is definitely going to point out of the page, will be equal to, for every loop that you have, you're going to get mu naught I over 2a. So if we take n times mu naught I over 2a, that'll give us our magnetic field. So that's a way that you can create a really powerful magnet, is simply by taking a lot of loops, wrapping them all around in a circle like this, forming like a donut of wire, a donut of like copper wire, for example, run current through it, and boom, you've got a nice strong magnetic field right at the center there. Does that make sense to everyone? Does anyone have any questions? So this is for loops. Last time we had learned for a long straight wire. I believe those are the two main. Nope, we're going to have one more we're going to learn in a second called a solenoid, but there's three primary versions of the magnetic field that you need to understand for this class. That is to say, the magnetic field created by loops of wire. And one is the ring, which is this one. One is the long straight wire, which is this one. And by the end of class today, we will learn about the magnetic field of a solenoid. We probably have to take a break now. Good time to take a break anyway. When we come back, we are going to be talking about Ampere's law, and we'll look at applications of it. Okay, so I'll leave this stuff up on the picture here, up on the board here, and we'll just take a break.